Good morning, friends. This is mechanical vibration lecture. That is about vibration under non-periodic forcing function. Actually, in our previous lectures, we have seen vibration under general forcing condition. But in today's lecture, we are going to extend our lecture to vibration under non-periodic forcing. So, what is non-periodic forces? So, these non-periodic forces are irregular type of forces are there. Impact forces are there. Some impulsive forces. Some ramp forces are there. So many types of forces are there. So we are going to see those things. So in the existing force, especially in the case of regular forcing condition, f of t is periodic. But now f of t is non-periodic, such that due to, for example, a blast force of the explosion, or the impact force on the structure. For example, if there is some impactor which fell down on the structure of any mechanical system, a different method of calculating the response is required. Okay, so some of the methods of solving such kind of forces are like the Fourier integral methods, the use of convolution integral methods, the Laplace transform methods, and also some numerical methods like Rank-Kutta method. So these are some of the methods which we use. So let's see. Actually, in our previous case, we have seen, especially for the regular forces, we have seen the Fourier expansion. So we used the Fourier integral method, and we implemented the Fourier's constant and the Fourier sign solutions for the solution of the force. So just this is a review of the previous lecture, one slide review. Okay, so when we see the periodic force of any general wave can be represented as a sine series, which is as a superposition of harmonic component of the various frequency. So, for example, this is the force mx dot plus cx dot plus kx is equal to f of t. This is a general equation, that is a general equation of motion. And then we have also a Fourier expansion, that f of t is equals to a naught over 2 plus summation of ai cos I omega t for I from 1 to infinity, plus bi sin I omega t for I from 1 to infinity. This is the Fourier expansion. Okay, this is the constant part, this is the sine and cosine part. Okay, so this is one of the representation, okay, for the harmonic component. So the response of linear system for this equation, for the linear part of found by superposing the harmonic response of each excitation. So here we can see this equation for two different cases. One is first order system and second is second order system. So for the first order system means if our derivative is the first order, that means it is maybe x dot of t plus some k type or a times x, which is equal to f of t type, that is first order. Then for the first order, we have the particular solution of which is a naught over a. This a naught ai bi are the coefficients which we determined in our previous lecture. Okay, so this is the solution for first order system. And for the second order system means like there may be acceleration, means x dot dot plus some k times x dot plus some constant a times x, which is equal to f of t type, that is second order system. For that, the equation comes like this. And here we considered damped system. Okay, this shows the damping ratio is there, spring constant or material stiffness constant is there, and the natural frequency omega is there. Okay, the damping ratio zeta is there. So for damped second order system, so this is solution for periodic force case. But most of the time, the force is not periodic. It is non-periodic forces. So for non-periodic excitation forces, usually there has some magnitude that varies with time. Means there is a change in magnitude as time goes. So for such case, we use convolution integral method. Convolution integral method is the one which we use for, especially, for example, in the case of impulsive forces. Okay, the simplest form of this type is impulsive force, a force that has large magnitude F, which acts in a very short period of time. Okay, that kind of momentum. Okay, impulsive force is large magnitude of force within short period of time. That delta t is very small. So let x1 dot and x2 dot denotes the velocity of the mass m before and after the application of impulse f of t. Then let's see some relation. F of t is equals to f delta t. Means this f of t is the impulse. We can represent this by I, no problem. Or we can use a kind of p, okay? So f of t is equal to f delta t. This f is force and delta t is the moment at which the impulse takes place, that very short period of time, which is equal to mx2 dot minus mx1 dot, which implies f of t is equal to integral of f dt for t start from some moment t to t plus delta t. Okay, so let's consider the unit impulse which occur at f of t is equal to 0, at t is equal to 0, which has a given f acting at 0 time. Okay, so for that, f is equals to the limit of delta t approaches 0. Okay, for the integral of t to t plus delta t, f dt, which is equal to f delta t. Gives 1. This means a unit impulse case. Okay, what we can see here is a Dirac delta function. Okay, this delta t is a Dirac delta function. Consider a system, single degree of freedom system of viscously damped spring mass system subjected to a unit impulse. Okay, let's consider a unit impulse case at time t0. As shown in figure A and the B, we have figure A, viscously damped spring mass system here. Okay, this is a system which is subjected to some impulsive force F of t, mass m, damper c, and spring elasticity k. Okay, and then we can observe his a unit impulse F of t at time t is equals to 0. Okay, almost at time t is equals to 0. This delta t is very small time. Okay, so the area under this curve f delta t is equals to 1. Okay, this is the f, this is delta t. So the area under this curve considered 1. And so for this case, for underdamped system, by considering underdamped system, the equation of motion is mx dot plus cx dot plus kx is equal to 0. This is an equation for zero force. Okay, but we consider the impulsive force here. Now, the solution of this equation of motion is, as we have learned in the previous case, x of t is equals to e raised to minus zeta omega nt as a whole under bracket x naught cos omega dt plus x naught plus zeta omega n x naught, no, this is x dot naught. The initial condition, this is the velocity initial condition. X naught is the displacement initial condition. So in most cases, we need two initial conditions. That is, x of t as t approaches as t is equal to 0, which is called x naught, and x dot of t as t is equal to 0 is x dot naught. So this is velocity boundary condition, initial condition, and displacement initial condition. Okay, so this applying the initial condition, finally we get this solution. Okay, so x dot naught plus zeta omega n x naught over omega d. Omega means damped natural frequency, sine omega dt. Omega n is just natural frequency, and omega d is damped natural frequency. So the relation between omega n and omega d is omega d is equal to omega n times radical of 1 minus zeta squared. This is the relation. And omega n is radical of k over m. And zeta is c, the damping coefficient. That is, zeta is equal to c over cc, so which is equal to c over 2m omega d. This is a damping ratio. Okay, so this solution is plotted like this. So this is the envelope of E minus zeta omega nt envelope. Okay, this part. This part is the envelope of this equation. Because as time increases, this part exponentially decreasing. That means this minus indicates that 1 over E raised to zeta omega nt. So as t increase, this value increase, so that 1 over this value, increased value, will give us this decreasing graph. So this is the envelope of this coefficient. And the total equation, or the this is the equation of this underdamped system. Okay, so this is what. Now, vibration response to an impulsive force. Let's see the impact force. So impact occur in a system of various mechanical systems, intentionally or unknowingly. Means, for example, the screwdrivers may fail on the structure of airplane. That can cause damage to the airplane. So that impact can be characterized by various parameters, like the impact force, the damage, the kinetic energy. Okay, so many parameters are considered in the case of impact. So for the impulsive force, F is equals to 1, as we have seen previously. It is this F is equal to 1 means this thing. Okay, here I'm going out of sorry. F is equals to 1 means this case. F is equals to this equation 2. So considering this equation, F is equals to 1 means, which is m of x dot of t is equals to 0 minus mx means we are applying the condition of near to time t0 from the negative side. Means this negative side means before impact and after impact. Okay, t is equals to 0. X dot of t is equals to 0 means it is just after impulsive force applied. And this is before, this approaching to 0 from the negative side of this graph. Let me show you. we have two regions here. Pointer. Okay. So from this side and from this side. Once from this side it is t is equals to 0 minus, we can call, and from that side it is t is equals to simply 0, or we can represent it as 0 plus, no problem, 0 plus. Okay, so that is a scenario. So mx dot t is equal at from t is equal to 0 minus mx t is equal to 0 from the minus side. So this from the minus side is almost 0. We have no impulse there. So we have left what? Mx naught. So this will be mx naught. Means, and also another, the boundary means the initial condition x of t is equal to 0, which is x naught. We have nothing there. So we found two boundaries here. Another boundary, x dot of t is equal to 0, means m of mx dot of t is equal to 0, which is x naught. So just taking this equation, only, we have this expression. So x naught is equal to 1 over m. This is initial condition for impulsive force. Means the two initial conditions are, I can express x naught is equals to 0 and x dot naught is equals to 1 over m. These are the two initial conditions. Okay. So substituting this initial condition in this equation, in the previous equation, this equation for underdamped case, the one which we have discussed here, by implementing this 0, okay, this is 1 over m, this one is 1 over m, this is 0, this thing is 0 because x naught is 0. Okay. Then the equation becomes, we can get this equation, 1 over m omega d e is the power of e raised to minus zeta omega n t sine omega dt, which is g of t. X of t, we just to differentiate our x of t. So let's give a name g of t. So this question number 7 gives the response of single degree of freedom system to unit impulsive force, which is also known as the impulse response function, and denoted by g of t. The function g of t is, we can see it in figure C. Okay, what is that g of t? Yeah, it is figure C there only. This is for g of t. Okay. There is some disturbance. It is because of my computer problem. If the magnitude of impulse is, we can represent impulse is I, or so we can simply take it as f of t, f only. So our x naught is equal to f over m. We can substitute it in the equation. So x of t is equal to f over m omega d e raised to minus zeta omega nt sine omega dt, which is f times g of t. So because we multiplied the initial condition x naught here, x naught. So our x naught is equals to 1 over m, and we multiplied it by f. So it becomes f over, means if it is the impulse is different from unit, there is some magnitude. The previous expression is only for unit impulse. But if the magnitude of impulse different from a unit, means having some f unit, x naught dot is equal to f over m rather than 1 over m. So then our expression becomes, expression in 7 becomes f over m omega t. So this change. So if the impulse I is applied in here, this I means f. This f, I'm just using f not to cause any confusion. Okay, instead of I am using f. So is applied at arbitrary time as shown in figure A. Look, now previously what we have discussed is it is applied only at 0 time t. But at some arbitrary time, after some time period t, the impulse happened here. This is delta t, means the moment of happening of the impulse. So f delta t is equal to f. But in the previous case, f delta t is equals to 1 there. That is the difference. So if delta t is equals to f means this here. But here, sorry for f delta t is equals to 1 here. This is unit impulse case. But in a recent case, f delta t is equals to f. This is the response for that. Okay. Impulse applied at arbitrary time t. Okay, or we can take some time period. Okay, so and the response starts from this moment. This is the response, and we have the envelope of this thing. The envelope of this thing also there. Yes, so someone can draw it like this. This envelope represents the expression e raised to minus zeta omega nt. Omega nt is this envelope. Okay. Yeah, so this is, and let's take an example of structure subject to impact load. So in the various testing of structure, an impact hammer with some load, impact load cell to measure the impact force is used to cause excitation. So as shown here. Okay. Assume the mass of the mass is 5 kilogram, the mass of impactor. The structural, no, the mass of structure, not it is the mass of impact. The damper, consider 10, okay. Stiffness of this structure is considered 2000. And the impact force applied in terms of F is equal to 20 Newton second. So this is the impact force which is applied to the structure. Okay. This is the hammer. Okay. So it is hammering like this. Under this, we have two different cases. When the impact is happen only here at the t is equals to 0, when t plus the time moment means different. This is we call double impact case. At t0 second, at t is equal to 0.2 second, and double impact. Okay. So this is the case. So how we can solve it? Okay, let's assume single impact at t is equals to 0. So F is already given with magnitude of some value. And at this moment, we can substitute only values. M is known, WD is obtained from WN. The WN is K over M. So we have this WN, natural frequency. And the damping ratio, C over 2M omega D. So for that, and which is equal to C over 2 radical Km. So we can get the damping ratio, it is unitless quantity. And the damped natural frequency is equal to natural frequency times 1 minus zeta square, which gives us this value. Means the value of natural frequency and the value of damped natural frequency are almost in the near point. This is very near to happen the resonance. Means resonance means if omega d over omega n is equals to 1, that is the point of resonance. So they are almost near. So what we can do, substitute the values, these values here. So F20 for the first case, F is 20. I'm sorry for this. So M is 5 and damped natural frequency is 19.975. So just substituting, finally we can get this equation. This is the equation. So running MATLAB program, we can find this solid line. So for underdamped case, you see here, the damping ratio is very small, 0.05 means very small. That is underdamped case. So this is the solid line represents the current solution. And this envelope, as I explained you, this envelope represents this component of let me show you. This is this component, okay, e raised to zeta omega n. Okay. So what will happen if it is double impact happen? For example, and here there is another impulse happen here. F1 is the first impulse, F2 is the second, another impulse. So how we can represent this second impulse? So T0 means the first impulse moment, and T greater than 0.25 seconds for another impulse happen. So for that, we use the summation of Fi m omega dE. So this summation implies the effect of first impulse also under consideration, and then second impulse. If there is another third impulse, we sum up all of them. Okay, so instead of t, we substitute t minus zeta for time period. So finally, we can get f of t is equal to f1 delta t plus f2 delta t. This delta t is the right delta function, as I said. So that x1 of t is equals to f1 m omega d et, means this zeta is 0.005, omega is omega n is 20. So zeta omega n, zeta times omega n gives us 1. So it is by default they are there. And another one is similarly instead of t, we use t minus time period t. So this is for second impulse. So this equation represents the first part of impact, and the second equation represents the second part. It is the sum of the first plus x1 plus the combination of x2. Okay, so this equation is represented with dashed line. These dashed lines or dotted lines represent the equation of motion of second double impact case. Okay, this is for double impact, this is for single impact. Now, vibration response to perfectly elastic impact. Now we are going to consider the dynamic case from our dynamic course. There is collision and impact. Okay, so let's consider mass m moving with velocity v1 strikes another mass, bigger mass m, of a damped single degree of freedom system. We have a damped single degree of freedom system. This is the system before impact happened. There is a small mass or an impactor. We call this as impactor. We call this as structure. So structure at rest, V1 at this moment is 0 because it is a stationary point, and this V1 comes or dropped over the structure and makes an impact. And then there are two probabilities for this thing. If the impact is elastic, then the impactor, once the impactor impact or collide with the structure and rebounds. Okay. Or if it is inelastic, the smaller mass will stick together with the bigger mass and move together. So there are two probabilities here. So let's consider the rebouncing condition. That rebouncing condition represents perfectly elastic impact. Means once the impactor, after impact, it rebound, will not stick together to the mass, either in opposite direction or in the same direction, the movement. So this is the scenario. So when two masses m and n moving initially with velocity v1 and smaller, bigger means capital V1 strike each other and attain the velocity v2 and capital V2 immediately after impact, as we can see from B here. So this is after impact process. Maybe it can move down, again this move down, or it can reverse. So to solve this problem, we must apply two principles. One is principle of momentum conservation, and another one is the principle of conservation of energy, that is kinetic energy conservation. In elastic collision, in perfectly elastic collision, both momentum and kinetic energy is conserved because there is no energy loss in the system. But in the case of inelastic collision, momentum may conserve, but kinetic energy will not conserve. Why? Because there is an energy loss. Means the kinetic energy is converted into damage energy in the system. Means they stick together and one of the body is damaged and another will be inserted into it and move together. So in this case, in the perfectly elastic case, we consider momentum is conserved and kinetic energy also conserved. So from that, we have this relation. Okay, from momentum conservation, we have impactor mass times velocity or initial velocity of impactor minus final velocity of impactor, which is equals to minus of the mass of structure times initial velocity of structure minus final velocity. V2, 2 represents after impact, 1 represents before impact. Okay. Because the velocity of the mass m and capital M are known to be V1 and capital V1, which is equal to capital V1 is initially 0. Why? Because it is in the state of rest. Okay. The only one which produced the motion is the small v1. So from that relation, we have v2, the velocity of structure after impact, which is equal to m impactor mass over structure mass times impactor initial velocity minus impactor final velocity, which is equals to mass ratio, that is impactor mass to structure mass ratio times initial velocity of impactor minus mass ratio times final velocity of impactor. This is a second equation. Again, from the principle of conservation of kinetic energy, we have energy is conserved, means kinetic energy is conserved here. That means kinetic energy before impact is equal to kinetic energy after impact. Here also, momentum before impact is equal to momentum after impact. From that, we obtain these two equations. And from kinetic energy conservation, we obtain this equation. That is half m v1 plus v2 times, means one can use this one also, half m v1 square minus v2 square, means it is for the impactor, velocity of impactor, mass of impactor, okay, which is equal to minus of half mass of structure times initial velocity of structure minus final velocity of structure. So this is momentum conservation, no, kinetic energy conservation, because there is no energy loss that occur in this case. Means the structure will not damage. Okay. So from the above question, we can finally find this V1 minus V capital V1. This is initial velocity of structure, which is 0, which is equal to minus of V2 minus V2. So this finally gives us initial velocity, because this is known velocity, initial velocity of the impactor, which is equal to final velocity of the structure minus final velocity of the final velocity of the impactor. Okay, this is the second, another equation. So equation number 4 indicates the magnitude of relative velocity of the mass remains constant. Okay, from here, the magnitude of relative velocity of the mass, v1 minus v1, this relative velocity, one with respect to another. Okay, this is also final relative velocity, which remains constant, and only the sign change. You see, there is a minus sign here. Because of that, there is a sign change during perfectly elastic impact happen. So the solution of equation number 3 means our equation number 3 is this equation, kinetic energy equation. And equation number 5, this, from this we can obtain the impactor final velocity is equals to the impactor mass minus structure mass over impactor mass plus structure mass times impactor initial velocity. So we are expressing in term, this V2 is unknown and V2 of the structure is not known. So the only known parameter is V1. Mass is known, mass of structure is known. So these are known parameters, and this one is a known parameter. So from that we can solve. And the change in momentum of mass m is given by m times x2 dot, means this is v2, small v2, the impactor mass v2, no, v2 minus v1 v1. So we can use this, which is equal to m minus m, means we substitute this change in momentum be substituted in this equation. So finally, this change in momentum gives 2 mass of impactor, mass of structure over mass of impactor plus mass of structure times V1. This is with the minus sign, okay. Here what happened? V2 means this part. Substitute V2 here. V1 means V1 itself, so that it comes like that. I substituted, instead of V2 here, this parameter. Here. V1 is 0 only, it is V1. So finally we can get this solution. So for the impulse applied to the mass m during the impact processes, F is equals to 0 to t, f of t dt. So which is equals to equal to the value given there in equation number 7. So F is equals to this. Now let's go to the equation of motion. So from Newton's third law of motion, the impulse applied to the mass m during impact will be the same as, but opposite in sign, to the impulse applied to mass m of the impactor. So mx dot plus cx dot plus kx is equal to f, so that f is equals to this, the impulse. So finally, we have, okay, what will be the equation of this type of expression? Means mx dot plus cx dot plus kx is equals to minus of 2m over m plus m, capital M, the whole times v1 delta t. This delta t is still the right delta. Okay. So this expression is equals to this expression. So the solution from our previous most lectures become this one. So f is this. You see, instead of f, we can substitute this thing. Okay. Yeah, this is f. There is some minus sign here. I didn't use. Okay. It is there, minus sign. This is the solution. Now, once we understand perfectly elastic collision, then let's go to inelastic collision or impact. Vibration response to inelastic impact. That is another second case. So let's consider mass m moving with velocity v1 strikes another mass m of damped single degree of freedom system, as shown here. So here, this is impactor mass, this is structure mass, and this impactor comes impact the structure, and both of them after impact goes together, stick together here. Here, the two bodies are stick together. So this is because one of the structure is damaged. For example, this impactor damaged the structure and embedded into the system, and they move together. So during this time, what will happen? Look, in this case, the change in momentum is equal to impulse. Okay, momentum conservation happened, but kinetic energy will not be conserved in this case. So m change in momentum, which is equal to mv2 minus mv1, means for impactor, which is equal to integral of 0 to 1 f of t dt. This is the impulse, where m is the impactor mass, v2 is the final velocity of impactor, v1 is this is v1 is initial velocity, f of t is the force applied during short duration, that means impulsive force, and the integral of this denotes the impulse. Okay, so let's see that. Since the mass m gets attached to the mass capital M, means structure mass, after impact, the impact can be considered to be perfectly plastic or inelastic impact. The two mass moves together and considered to be subject to impulse with change in velocity of mass. So from that, the impact force F of t is internal to the system and can be assumed to be 0. Okay, so from question 1, we can m1 v1 plus capital M1 v1, which is equal to m plus m. Means at this time, m plus m, both mass together, then they have common velocity. Vs is a common velocity. Vs is equals to common velocity. Common for structure and the impactor and the structure after impact. So that Vs is equals to m over impactor mass over impactor mass plus structure mass times v1. v1 means the initial velocity of the impactor. So Vs is unknown. We know mass of structure. We know initial velocity of the impactor, so that we express Vs in terms of these parameters. Now, the equation of motion for the combined system is m plus n times x dot dot plus ex dot plus kx is equal to 0. This is somehow similar to kind of relative movement, like in the case of seismic case, earthquake case. We register the values in terms of relative movement of the base and to the structure. So our equation of motion from free vibration, as explained above, it is like this. Okay. But so this gives us, because x naught is 0 in this case, x naught is equals to 0, and we have only some x naught dot initial velocity, which is there. X of t is equals to 0 is equal to x naught. So only x naught part will remain. Okay, so that m over v1, because we have vs here, m1 v1 over m plus m omega t. This is f of s. Okay, so this is the solution for this case. Another important thing, the third case is numerical method. Means most of the time we express differential equations in terms of numerical method. because this analytical method so far discussed are somehow tedious in some cases. So in order to solve such tedious analytical equation, we use numerical simulation method using various softwares. Okay, so there are many softwares which are designed to take care of such numerical methods. Among them, we use rank-Kuta method as one of numerical methods. So rank-Kuta method, we express the second order differential equation to, we reduce it to the first order differential equation. It has a lot of useful applications, but reducing it to first order. So how we can do, actually with some prescribed initial conditions are there. Okay, so x at t0 x naught and x dot at t0, which is x naught dot. So that are the initial conditions which you use. And then how we can reduce, we let, for example, x1 of t is equals to x of t. Then x2 of t is equals to x1 dot of t. This means what? X dot of t. So this x2 is expressed in terms of the first order. So that that implies x2 dot of t implies x dot dot of t. Yeah. So the equation, the dynamic equation, mx dot dot of t, which is equals to cx, we use, just bring it back to this side. So minus of cx dot t plus minus kx of t plus f of t. So once this x dot dot of t means x dot of 2, means we substituted this part here. X dot of t means x2 of t. X dot of t means x2. This is x, x2. Yeah, that is x2 of t. X2. This is by this. Yeah. So x of t is x1. X1 of t. So once we change it, now the second order is changed to the first order differential equation. Well, this differential equation is mx dot x dot plus cx means x2 plus kx1 f of t. So, and another x2 of t is equal to x1 of t. So we have two equations, and one is this mx2 of t. Okay, here m is already, sorry, this m is 0 only. Okay, x2 of t is equals to x1 dot t. X dot of t is equals to minus of c over mx2 of t minus k over mx1 of t plus 1 over m f of t. So this is two equations, equation 1 and 2. So from these two equations, we can express this equation in the vector form. Okay, so vector x of t is equal to f of x of t. So here there is force and other quantities combination. So that means x of t is equals to x1 of t and x2 of t, which implies x dot of t, vector x dot of t is equals to x dot 1 of t, x dot 2 of t. So this is the representation for the two equations in matrix form. Finally, f of x t implies f1 of t and f2 of t. That means f1 of t is equal to x2 of t, x2 of t. And f2 of t is equals to minus of km, this quantity. This quantity, okay? We put this quantity here. Then the solution using the Rank-Kutta method leads us expression like this. In most of numerical methods, improved methods are presented like for equation x of t of I plus 1 means the next iteration of I plus 1 is equal to xi plus delta xi. Means xi plus 1 implies the x at time t, which is equal to ti plus 1. Xi implies the current time t is equals to ti. And incremental, this is not xi, but t is equals to ti. Ti, sorry, this is ti. So the increment added to ti. If the solution x of t is to be found over the time interval 0 to less than or equal to t, t is less than or equal to total time, this total time, then the time t is divided or discretized into a small incremental time, delta t, which is equals to sometimes given in h. Okay, so we have to discretize it. T naught is equal to 0, T1 is equal to delta T, T2 is equal to 2 times delta T, T3 is 3 times delta T, Ti is equal to I times delta T. Okay. And then the Tn, which is equal to T is equal to n times delta T. So this is the method of dividing time in order to get appropriate iteration. So in the Rank-Kutta method, the approximation formulas used for obtaining solution for xi plus 1 from xi is made to coincide with the Taylor series expansion. So this is the Taylor series expansion of x of t plus delta t, which is equal to xt plus x dot of t delta t plus x dot of t delta t squared plus and go higher order derivatives. Okay, so most of the time we truncate it, the higher orders are truncated, and we consider them as some error terms. Okay, it is considered as some error term. Okay, or n of t delta t. Okay. So error terms are neglected, and we most of the time give emphasis to these terms. Okay, so this Taylor series expansion. If the force, let's consider the force of the Rank-Kutta method, which is most commonly used. So for that, what we can do? Let's start from the initial conditions x naught or the vector x naught, which is x naught and x dot naught. That means x of t is equal to 0 and x dot of t is equal to 0. This initial condition, okay. And then vector xi plus 1, which is equal to xi plus 1 over 6 vector k1 plus 2 times k2 plus 2 times k3 plus k4, where these k's are, how we can express k's, where so k1, this del h means here h implies delta t. Okay, delta t. F of xi ti implies these quantities. Let me show you this quantity. f of xi, sorry, yeah, f of xi ti implies these quantities. Okay. So k1 hfi xi ti, k2 delta t f vector fi xi plus 1 over 2 k1 of ti plus half h means half delta. Again, K3 also expressed in terms of K2, and K4 is expressed in terms of K3, like that. And the final T is Ti plus 1. Still, it is Ti. Okay, so this method is stable and self-starting, that only the values of vector function at single previous time station is required to find the function value at the current time situation. So let's take one example, a response of using the Rank-Kutta method. For example, we have this equation. Okay, for single degree of freedom system subject to force with equation of this type. F of t is given like this. So this is M, this is C, sorry, this is K, and this is F. Another important thing about the initial condition x naught is equals to 0 and x dot naught is equal to 0. Both displacement and velocity initial are 0. And the total time is considered 20 seconds. That is the total time that impulse force happen. And we can discretize, divide the time 40 steps, means n is equals to 40. For 400, sorry. N is equal to 400 means what is delta t? We can find delta t. Delta t is equals to total t over n. That means 20 over 400. 400. That is delta t, which is equal to 0.05 second. This is discrete time interval in which analysis will carry out. So now, from the given expression, the solution becomes f vector f of xt is equals to f1 of t, f2 of t. f1 of t is x2 of t, and f2 of t is just dividing all these equations to m. We have this expression, x1, x2 is here x2. Okay, so here yeah, f of t is actually 200. We can represent 2000, sorry. Okay, this represents stiffness. This represents stiffness. Okay, this represents the damper. This represents mass m, and f of t is equals to, we can put it 2000 here. Okay, I can substitute it 2000 here. 2000. Okay, and initial conditions are already given 0. Sorry. Now the response is computed over the time domain, 0 to t. T means 20 seconds. The time duration of these 20 seconds. So divide it so that we can get 0.05 second is the delta t. Now, from this t naught is equal to 0 initially, t1 is equal to 0.05, t2 is equal to just 2 times, 3 times, 4 times, and go to t3 99, which is equal to 19.95 seconds. And the time of 400, n is equal to 420. So we have solution like this. For step time, 1, 2, 3, 10, 399, 400. What is x1? 1 is considered the 0 time. So in 0 time, we have nothing. In 1 second, we have this relation, this solution. And 3 means in this case 0.1 second. In 0.1 second, we have x1 is this, x2 is this. So from where this x1 and x2 comes? From this equation. Okay, from this equation, x2, x1. They are expressed in terms of x2 and x1. So this is all about this part of solution. In the next time, we will meet with second order, means vibration of 2 degrees of freedom. And we'll go for multi-degree of freedom vibration in the next. Thank you very much for watching. And